Ladies and gentlemen, our next session will commence in 3 minutes, so please kindly take your seats. And for audience who join us online, please get ready for our next session. Thank you. And I think I've seen our speakers online already, so I would like to welcome you later. Please, thank you for your patience. Ladies and gentlemen, welcome back to QCrypt 2022. This session is Invited Talk, DIQKD Talk Series, and we have invited 3 speakers for this session. And for now, I would like to welcome the session chair, Professor Feihu Xu. Professor Xu, can you hear us?
Hi. Yes.
Hello. Yes. Please proceed.
Okay. Well, can you turn off the music? You turn on music.
我们可以先音乐先关掉，谢谢。
Okay. Okay, that's good. Okay. Good morning, good afternoon, or maybe good evening for people from different place. I'm Feihu Xu from University of Science and Technology of China, USTC. So it's a great honor to chair this session. So this session, as you see from the schedule, is a special session focusing on device-independent QKD. So several people may see the recent important progress on theory and also experiment DIQKD. So it was demonstrated by 3 groups around the world using different platforms. So today it's a great honor we invite the speakers from these 3 groups. They are Dr. Wenzhao Liu from USTC and Harald Winfeter from Munich, and also Nicolas Sangard from France. So I think they will talk about the progress on their work. So let's start. According to the schedule, the first speaker will be Wenzhao. Maybe you can share your slides. So these are 3 invited talks. Each talk will 25 minutes plus 5 minutes Q&A. Wenzhao, please.
Can you see the slides?
Yes, very clear.
Okay. Thank you for the introduction. I'm Wenzhao Liu from USTC. It's an honor to share our recent experimental progress on the device-independent quantum K distribution here, which has been recently published on the PRL. This work is done together with our theory collaborators also in USTC. You can also find the related theoretical work online. All right, first let's start with the quantum key distribution. It's a protocol to share random numbers or named secret keys between remote parties. As we all know, the security of classical communication protocols are based on the classical computational assumptions, which is threatened by quantum algorithm and recent rapid improvements of quantum computers. Compared with the classical protocols, the security of QKD is based on the law of quantum physics. And besides, several fundamental assumptions are required, including authenticated public classical channels. The classical communication channels must be authenticated using an unconditional secure authentication scheme, and also characterize devices to implement the protocol, and trusted input and the security of output, which means that if cannot physically access Alice and Bob's encoding and decoding devices, the trusted input can be realized by quantum random number generators, QRNG, to generate truly randomness to decide the measurement settings. However, in practical scenarios, it is hard to guarantee the third assumption. The state preparation and measurement could be imperfect. Also, some talented protocols have been found, such as the measurement device-independent protocol and the recent developed twin-field QKD, which is another form of DIQKD. For example, these figures are our group's related work on TF-QKD present this morning. Well, it should be noted that one fundamental assumption in DIQKD is that if cannot interfere with Alice and Bob's state preparation processes, and also the devices used in the implementation should be well characterized. The various quantum hacking experiments that have been conducted over the past few years have shown that many implementations of QKD fail to satisfy this assumption. Now we come to the device-independent protocol. The main purpose of the device-independent QKD is to solve various security problems caused by imperfect devices and the implementation. In contrast with traditional QKD, no knowledge of devices is required, and the security of the device-independent QKD is based on the statistics, which is the Bell test. A typical model for DIQKD is shown in the figure. We assume the experimental devices for Alice and Bob are black box. The two parties could be distant separated, and X and Y are the inputs for Alice and Bob in each round, respectively. A and B represent the outcomes. A typical protocol is that X has 2 values and Y has 3 values. A and B have 3 different results. In each round, Alice and Bob choose randomly. If Y is 1 or 2, then results of these rounds are collected to do Bell tests. If Y is 3 and X is also a fixed input 1 or 2, the results of these rounds are used for secret key generation. Similar to QKD, device-independent QKD also requires these basic assumptions. In fact, these assumptions are obvious for all current quantum communication protocols. Well, the assumptions for devices are no more required. The security of device-independent QKD is based on the Bell test. However, the results of Bell tests should be valid, which means that no extra assumptions are needed for a practical Bell experiment. So in practical scenarios, we need loophole-free Bell tests. There are some assumptions in the Bell experiments. First is the locality loophole. It describes the choice of the measurement basis of one party may affect the measurement of the other party in each experimental round, which is typically closed by keeping the related events space-like separated. The second is the fair sampling or detection loophole. It is mainly due to the loss caused by the imperfect devices, which makes imperfect detection of all generated entangled pairs. This can be solved by increasing the hiding efficiency, and also there are some other loopholes. Freedom of choice and collapse locality need to be solved. Considering the significance of the first 2 assumptions, The experiments without locality loophole and detection loophole are usually called loophole-free Bell experiments, and it was first realized in 2015 by 3 different groups with NV centers and photons. An observation of a violation of a Bell equality implies that the measurement outcomes contain some general randomness, and also it is easy to think that the solution for the trusted input could also be upgraded from QRNG to device-independent QRNG. Our group implemented several device-independent randomness generation and expansion works in recent years. The randomness generation is easy to understand, while the randomness expansion is a protocol to make output randomness surpass input. Given trusted random seed, we can generate more and more randomness with device-independent security by means of device-independent randomness expansion. Okay, here are some milestones in the development of device-independent QKD. In 1991, Arkert proposed the protocol named E91. It is the first QKD protocol based on EPR pairs and the violation of Bell's inequality. But the idea of using quantum non-locality to guarantee security was not fully realized at the time. It was in 1998 when the problem of untrusted source was first solved by Myers and Yale through the concepts of self-checking source and tests. The essence of the idea is that if the experimental statistics satisfy certain conditions, the state must be EPR pairs. In 2005, Barrett, Hardy, and Kent quantitatively linked the violation of Bell inequality with the secret keys, and several secret proofs against different types of attacks were finished over the next few years. And in 214, the first complete security proof for DIQKD was finished against general attacks. And in 2018, the so-called entropy accumulation theorem, EAT, was proposed to convert the sequential process to the independent and identical distribution scenario, IID scenario, for entropy calculation. And it provides the theoretical groundwork for experimental demonstrations of device-independent protocols with finite data analysis. Okay, the milestones mentioned above are all about the development of theoretical DIQKD. Only recently did the experimental DIQKD had a breakthrough. There are 3 different experimental DIQKD works based on different matter systems have been published recently, which first realized the proof of principle demonstration of DIQKD. Besides our experiment based on the photonic system, the group of University of Oxford realized a demonstration of device-independent QKD based on trapped ions, and the group in Munich used trapped atoms. They have similar systems. The system established entanglement between 2 ions or atoms by entanglement swapping. As for the details of these 2 experiments, please refer to the following invited talk from Professor Harald Weniferter and Professor Nicholas Stangard. All right, this is a quick overview of the talk. First, I will introduce the main idea of our protocol to realize device-independent QKD. Then I will show the experimental setup and the results obtained. And the last part, I will give a brief discussion of our work. First, let me introduce the random post-selection, which is the main idea of our protocol. In the scenario of the device-independent, we need to close the detection loophole in order to realize the loophole-free Bell test. The specific method is to count all results obtained in the experiment into the statistics, regardless of whether it is detected or not. But obviously, due to the imperfection of devices, this will count a large number of undetected events, especially considering the SPDC source, which is mainly used in an entangled photonic system. Undetected events are unavoidable, even with perfect efficiency. The large number of undetected events contain few entropy, but a lot of errors. So it was natural to find a suitable way to extract subsets with more entropy from the measurement results. The figure shown is a model for the device independent experiment. According to the outcomes of the detector, we divide the detection results into 3 types: bit 0, bit 1, and no detection. It is easy to find that the joint detection results consists of 0 and 1 should contain more entropy, while the other results contain little or none due to the no detection events. So the main idea of the random post-selection is to only extract randomness from the post-select subsets. Someone might suspect that this could lead to the opening of detection loophole. Well, since the amount of secret entropy is evaluated from the results of the non-local test, in which the entire data set are involved, the detection loophole will not be left. The above operations are performed on the key generation rounds, which is aimed to reduce the bit error rate. The specific procedure of the protocol used in our work is shown in this slide. Besides the random post-selection, the method of noisy preprocessing is also involved. We only use a part of the results in the fixed basis for key generation, such as x equals 1 and y equals 3 in the table. It should be noted that the protocol used in our work is not a CHSH-based protocol. For DIQKD protocols, a common type protocol is to link the key rate with the CHSH value. The protocol introduced here is an optimization algorithm based on the whole dataset, which can be understood as finding the optimal Bell-type inequality based on all joint probabilities, rather than based on a few fixed items like the CHSH inequality. This method can reduce the requirements for the Bell value and the experimental devices. The first step of the implementation is to choose testing rounds. This requires some pre-shared randomness for Alice and Bob, and then they will get the outcomes in the selected basis. Since there are some no detection events, we treat them all as bit 1. The next step is the random post-selection. We keep all bits 0 for both Alice and Bob, and keep the bit 1 with a probability p. For example, the red bit 1s are discarded, and the green ones are kept. It should be noted that the value of p calculated by optimization is often small, since in all bits 1, the undetected events are the majority, so it makes sense. And then Alice and Bob announce the discard rounds via an authenticated public channel, and keep rounds not mentioned by either party. Next, Alice alone flips her survived bits with probability pt. This is the step of noisy preprocessing. Although this will increase the bit error, the random bit flipping will reduce the information that you could obtain from the results, thereby increasing the amount of the secret entropy. And the last step is that after one-way error correction and privacy amplification, we could obtain the final secret keys. Besides the random post-selection and noisy preprocessing mentioned, we also combined the numerical methods to estimate the key rate via the von Neumann entropy instead of main entropy. This method is developed by Peter Brown et al. And has also been published online. Okay, next let me give a brief introduction of our experimental setup. We use a spontaneous parametric down conversion photonic source to generate entanglement. And the detector we used is the superconducting nanowire single photon detector. It works under 1 Kelvin and shows a detection efficiency of about 97%. The pulsed pump laser has a wavelength of 718 nanometer and a repetition rate of 2 MHz. The entangled source generates Polaroid photon pairs with wavelengths about 1,560 nanometer and are distributed to 2 parties, Alice and Bob. In each side, Alice and Bob perform measurements. Here are some discussions need to be made. Alice and Bob are both close to the entanglement source in our setup, and they connected to the entanglement source through spatial light paths. It seems like this makes the locality loophole unclosed, since the related events are too close in space. However, let's recall the fundamental assumption of device-independent protocol. It requires that the information about the input choices and output results of one party must be unknown at any other location, including Eve's location, which means that only satisfying the space-like separation is not enough for the realization of this assumption. Therefore, the closing of locality loophole is not so important in the device-independent scenarios. In a practical implementation, some shielding techniques may be a solution to this assumption. However, considering the essential photonic channels from entanglement source to both parties, perfect shielding might not be realized experimentally. The using of spatial light passes connecting source and measurement is aimed to improve the efficiency, because it reduces the need for photons to be coupled into fiber before being measured by the detector. Another discussion is that we only use value place to alternate the measurement basis. Although this does not meet the requirement for random basis selection. As a proof of principle work, the focus of our work is to prove our system have the ability to generate secret keys. The reason we did not perform the random base selection is that it will lead to about 1% extra efficiency loss, which makes the system working as a major point of efficiency threshold. Here are some numbers about our experiments. These are the prepared quantum state, the optimized measurement settings, the horizon efficiencies about 87.5%, and the quantum state fidelity about 99.5%. It should be noted that for the photonic system, every little bit of efficiency improvement or reduction is very important. Here is a list of some important theoretical works in the development of DIQKD. They are all based on the SPDC source and give a corresponding efficiency threshold for the implementation of experimental DIQKD. Because of the time, I will not show every work in depth. It should be noted that all thresholds here are based on a perfect quantum state, which is a state with a fidelity of 100%. Although generating a high fidelity quantum state in photonic system is not so difficult as in the arrays and atoms, but it can only guarantee a fidelity of 99% to 99.5%. However, the requirement of efficiency will increase rapidly as fidelity decreases. This is a table containing the efficiencies of some reported photonic experiments based on the loophole-free Bell test. You can find that our experiment is the state of art. But even so, we also just finished a proof of principle demonstration. Okay, here are the results of our experiment. As mentioned before, we have 6 different combinations of measurement settings. For each one, we implement the same number of rounds and then get the raw data. Before the calculation of the key rate, due to the
Well, seems
My connection's got some problem again.
yeah, we lost the speaker.
I think he will join us online again now. Okay.
Okay, can you hear
Welcome
me?
back.
Yes. We can,
Okay.
I can hear you perfect right now. Oh, would you like would you like to turn off the camera maybe for a better connection quality?
Camera, what about now?
Yeah, maybe you can turn off the camera and you can
Turn
start
off the camera.
sharing. Yeah, and start sharing your slides.
Okay. The connection is unstable. Yeah.
Right. Maybe you try to reconnect again. Let me see if Wenjia is still online or we lost him again. We lost him again? Okay. So maybe he will try to get online. Let us try to connect with him. Oh, Wenjia is back online with us. Ooh. I think I've seen him for like a second. And
Okay.
okay.
Very good.
Is it okay now?
I think so.
Yes.
Yeah.
Oh. Maybe I go on in this slide.
Yes, please.
Okay. Oh. Oh, maybe. Yeah, this. Okay. Here are the results of our experiment. As mentioned before, we have 6 different combinations of measurement settings. For each one, we implement the same number of rounds and then get the raw data. Before the calculation of the key rate, due to the statistical fluctuations, the original probability distribution may not meet the no signaling conditions. We need to first find the distribution that satisfies the no signaling condition, which is closest to the observed results. And then we could follow the protocol to generate the secret keys. In our work, due to some limitations, we only calculate the key rate and the specific implementations steps are ignored. The limitations include collective attack model and infinite data analyze. The collective attack model is to add some extra assumptions to the eavesdropper's ability. The infinite data analyze is to calculate the key rate calculation in the asymptotic limit, that is, after sufficient number of experimental rounds. We simulate the fiber loss in a practical quantum network by varying the fiber lines, and shows the feasibility of generating a positive key rate after 220 meters fiber. We also try to get an optimized CHSH value, but it could only reach 2.05, which is much less than the value in atom and the iron system. That is one of the reasons why our work is so tough, and we developed a protocol that not based on the CHSH value. The table is our results with different fiber lengths, and the figure shows the efficiency threshold in different cases. The purple curve is the theoretical predicted results under our experimental conditions. If we consider a perfect quantum state, the threshold can drop below 700%, can drop below 70%. Okay, let me give a brief summary of our work. We made the first proof of principle demonstration of photonic DIQKD. The photonic implementation enjoys the advantages of high-rate entangled photon generations in the telecom wavelengths, which is important for the practical applications involving quantum memories or quantum repeaters forming a quantum internet. Also, our work has some limitations. The collective active model, the infinite data analyze, and the manual measurement settings are the most important ones. These limitations are mainly depend on the efficiency. We note that a recent theoretical work may suggest a solution for DIQKD with finite data analyze against a general attack, but it also requires at least about 90% efficiency to be possible. So the next step in the development of photonic DIQKD requires both experimental and theoretical progress. Okay, last but not least, I would like to thank all the collaborators and the people who have helped us with this work. Here are the photos of our Chance group and Jeremy Pan's group taken about 3 years ago. Yeah, that's all. Thank you for your attention.
All right. Thanks, Wenjao, for the talk. I guess we have 3 to 3 minutes left. We can take some questions.
Questions here? Or online? You can leave your questions in the chat box. Oh, we have a question here on site. Yes, please.
So I just wanted to ask, so when you make this estimate for the telecom fiber, so this will require a dark fiber?
Sorry, require what fiber?
So I think like in one of your results, you say that in principle, you can get key from 220 meters of telecom fiber.
Yes.
But this would require a dark fiber.
A dark fiber is what is a dark fiber? I'm not aware with this.
You can have other things in the, like it has to be the only thing that's going through it. Like you cannot use actual telecom fiber, which is also running some other classical data.
You mean the dark fiber is without any other noise in this fiber, just the signal?
Yeah.
It depends on the noise level of the system. In our system, just now the noise level is not a big issue. So I think now we just test you use the telecom fiber to do this experiment, but we didn't test that if we add some noise in this fiber, if the particle will also work. So maybe we will have a try. Yeah, I'm not sure.
Yeah. Okay. Yeah. Thanks.
Okay, thank you for the question and thank you for answering. Any other question here? Do we have any questions online?
Yeah, any question online? Okay, I think if no questions, we can go to next speaker.
Please.
Yeah, okay. Then our next speaker will be Professor Harald Winferter. I think he will talk about their experiment use trapped atoms. Please, Harald. So Harald, you need to turn on your
microphone, please. Thank you.
Microphone.
Sorry.
Oh yeah.
So thank you very much for the invitation here, and I'm happy to show you our experiment now on this device-independent QKD. Actually, it was a collaboration with team from the NSU around Charles Lim, who organized it, who brought important and necessary theoretical input then. And of course, it's also important to mention all the work from the previous teams, which then, of course, laid the foundations for the experiment and also for the more recent results. There are also input from even more people coming on, but then perhaps it will continue. Okay, so what I want to show you is how we can generate the atom-atom entanglement via first starting off with atom-photon entanglement and then employing entanglement swapping to get something like an heralded atom-atom entanglement, which is crucial for really loophole-free Bell tests. And then I'll show you how to use this now for the device-independent key distribution. And yeah, at the end, I'll make some outlook on where it can go next. So everything started, to my opinion, already with this with Bell's paper on the Einstein-Podolsky-Rosen paradox. Like when showed us already before, the Bell inequality is more or less, or Bell test is crucial. And to me, the Bell test is really something important because for the first time, it really enabled us to test whether nature can be described by a local and realistic theory. So it's not, I mean, local realistic theories are all the classical theories, and whether the quantum world indeed can be described like this as well. And actually, Arthur Eckert then already built upon this entanglement, which is necessary for this test, his protocol, where he showed then effectively that if there would be some local information available along the quantum channel, then we would lose the violation of the Bell inequality. And that's a nice feature now from the device-independent proposals there, what had been mentioned already before in detail, that they even extended this concept that if there would be any knowledge about the measurement results or about the future key available somewhere locally, so not only along the quantum channel by some eavesdropper, but even if the eavesdropper would sit inside our quantum devices, then we would see this as the yes, the violation of the Bell inequality is not possible anymore. And this then, of course, relaxes a lot of the security assumption, and especially that we do not need any trust in the devices required. So even the eavesdropper could have already made some manipulations to them, and we would notice it. Of course, this only concerns the quantum part. So we still have to certify then also that the classical part of these devices is secure, but this is a task which is similar to all any communication devices anyway. Okay, so, but as mentioned, there are always these loopholes in the implementation, especially the independence of the observers, the efficiency especially, and then of course also the randomness. And was, since a long time, it was always the goal to somehow close these loopholes, already in the experiments by Elias Peyer and his co-workers. But then in around 2000, there have been two experiments, I would say, which really closed some loopholes, but of course only one at a time. So in Innsbruck, we really could separate the two observers by 400 meters, which gives you about a microsecond time to perform the measurements, and that's, yeah, let's say, plenty enough. So to really separate, to really provide a space-like separation between the observers. And around the same time, Monroe and Dave Wineland's group, they made the first measurements on entangled ions with an efficiency effectively equal to 1. So actually this already motivated long time ago our experiments. So the idea is that if you have an atom which starting from some excited level has two options for decay, and if these two options then are have a different spin, then these atomic state levels have a different spin, then the polarization of the light emitted will be entangled with the state of the atom. Okay, and if you now have two such atoms, then if you bring together the two photons and perform a Bell state measurements, you use this protocol for the entanglement swapping. So it's like quantum teleportation to generate the entanglement between the two atoms. Then. Okay, so it's conceptually very different from the scheme what we saw before, where you start off with a source of entangled pairs and distribute them. Here we rather generate the entanglement between the two atoms via the entanglement swapping protocol. But this entanglement swapping protocol gives you the additional option that you now have this heralding signal. Always when you see this signal, then you know you have the entanglement and then can start with the Bell experiment. And then you make the measurements on the atoms, and effectively with this fluorescence detection, you can get a very, very high efficiency on this. And if there is some inefficiency that you lose the atoms or whatever, then this would only show up as an additional noise. Effectively, you really give an answer to each and every challenge what you have from this heralding signal. Okay, so in the experiment, it's a little more involved. So here we have a rubidium atom. It's picked with an so-called dipole trap, actually. So this light tweezers out of a cloud of atoms and then hold tight. Then we excite it and we collect the fluorescence into some glass fiber and bring it together via interferometric Bell state measurement, or for the interferometric Bell state measurement on this fiber beam splitter. And for example, if we see a detect a photon in each of the two outputs, we know that we have projected the photonic state onto the psi minus, onto the singlet state. And with this, we project then the atoms also into the singlet state. So here you see again something like 400 meters. This is actually the picture of our campus in Munich, of the LMU in Munich. And there, starting from our lab, there are lots of cable channels. And fortunately, we got also another small lab in the economy department, and the distance is just about this 400 meters again. And this then enabled us to select some random directions chosen by some quantum random number generator to perform state analysis on the atoms after you receive this ready signal from the Bell state measurement. And with this, you can then make some Bell tests. You obtain some violation of the Bell inequality, so the CHSH inequality is limited to 2 and values below 2. And for quantum systems, you can then achieve a value larger than 2, and with enough rounds, like 10,000 rounds in those days, you get the value small enough so that you really can say that the probability for such a locally hidden variable theory is negligibly small. And you can make other tests, like mentioned before as well, some quantum random number tests, or then also you can prove that the link between the two labs now is really a quantum link, what you cannot make with any classical means. So this was actually a collaboration with Nicolas Angras back then, still at the University of Basel. But these experiments, they have not been good enough for device independent QKD, simply because, I mean, to violate the Bell inequality, you need some S value, but I mean, not a very high S value. For the key distribution, to really get the positive key rate, you need, of course, a very low quantum bit error ratio, and therefore these experiments those days, I mean, they have been way too lots of noise. Okay. So that's our old data. So lots of improvements have been necessary, especially on the experiment to get higher fidelities, lower quantum bit error ratio, and even higher S value. And then the other improvements, of course, have been these new noise-tolerant protocols. So on the experiment, the one crucial improvement was a new objective to collect the light emitted from the atom with much higher sampling efficiency, so you get a higher rate, but also the beam to hold the atom tight was much better defined, and then it causes less heating, because even in this small trap, the atom of course will still move a little, and if the beam is not so nice, then this actually leads to a little more heating. So this was reduced also then. The magnetic fields, they have been kind of compensated somewhat differently using guiding fields, because actually the subway just crosses our experiment along this main road, what you saw in the picture before, and causes, of course, a lot of magnetic fields and also other sources in the labs, etc. They have to be somehow kept under control. And because of the better tweezer beam, then we also could lower the trapping potential. So all this then leads already to a better quality, but a huge improvement also came by an improved time selection. So if you look closer to the level structure of the rubidium atom, then of course it's not only such a nice two-level system or three-level system, what I showed you in the introduction, but rather you have many more levels which cause then other transitions, off-resonance transitions, other emissions of photons, which simply disturb then the whole process. So it's not the ideal single photon source, of course. It's ridiculously good, but still, I mean, you have some disturbance, and that's already good enough to reduce then the quality of this Bell state measurement, especially. And so, but if you then deselect some of the events, and you do this already before you start off with your experiments, you decide on this time. So that's also that it does not reduce any quality of the loophole free test. So you do this before already, you know that it's better to just omit all these events in the beginning of after the excitation pulse, but only then really use this fluorescence from the atom, from the states, what you really can use. And if you confine yourself to just this acceptance window, okay, you lose a lot of light and a lot of events, possible events, but then the fidelity goes up by almost 10%. This, of course, then was very crucial to all the experiment. The improvements from the theory side have been this noise-tolerant protocol, and the NUS team, they noticed that if you add, or if you use two bases for the key exchange, so more or less two quantum bit error ratios, you get a much better noise tolerance. So effectively, we have now two directions from what Bob has to measure anyway for the Bell experiment, and then 2 and 3 together. These directions, they are used to make the Bell test. But now if Alice just doesn't use only one of the directions of Bob to have some alignment and to get a key to have the perfect correlations, but then another one as well, then the protocol becomes much more tolerant to noise. So you see that compared to the old line here, you get a much better dependence, and then effectively you can hope that you get into this region where you really can create keys. So again, now what we need is first the single atom traps, and then some light which is emitted, which is entangled with the state of the atoms on both sides. And then we bring the light together on the Bell state measurement. So it does not matter, it sits in the lab of Alice, and the light from Bob is brought over here. And so Bob starts a little earlier if you want this, so that the two photons emitted really just then interfere here in the Bell state measurement. And then once you have this ready signal, you choose some random numbers from the local quantum random number generators and store your results some local storage, what you then use to generate the key. And then what was already mentioned as well is the shielding of the lab. Of course, I mean, we somehow assume or can now assume that we are kind of isolated, and one of the assumptions is that there is no, that there is no information sent from Bob to Alice and vice versa. I mean, we still have actually a space-like separation in our experiment anyway, but in addition, so that there is no option for an eavesdropper which sits here in this quantum channel, so that there is no option, we also include some shutter, which closes more or less the light channel when Bob makes his fluorescence measurement. There is no problem with Alice setup, because here there is no, all the light goes to the detectors and not to the channel. So the two observers, they are really separated also concerning light, which would leak into the quantum channel. And then you get these results. So here you see the measurements of the correlations. So they are always done in the different bases. And from these data, in the green shading, there you get then the result, the data for the Bell test, and where we have perfect correlation, these settings then can be used to generate the key. So in the experiment, we do not have a very high collection efficiency, still even with the higher, with the improved optics. But yes, as I mentioned, we then decrease the quality of or the rates right away with this time selection. So in 75 hours, a little more than 3 days, we observed 3,300 and something events where we really could generate entanglement. But therefore, the visibility was really nice. So this visibility number is now just a fit to this data. Unfortunately, the noise is not really fully symmetric. So, and actually the measurement angles, they have been designed for maximum violation of the Bell inequality. So here you see that the perfect correlations, they are somewhat lower than the visibility tells us actually. But still they are high enough for this test, as you see now here. Because now our data are well inside this region. Actually, they're even now inside the old limit for the device-independent QKD, but of course always in the assumption of the asymptotic analysis. But still, with the asymptotic analysis, we now get 7% of key per entanglement event. Which sounds low, but I mean, it has to be related to the 25% what you can maximally get with this protocol. Okay, so because here you see it again, just 1 out of 4 instances really here of these settings, 1 out of 4 just gives you a key, and the others either can be used for the Bell test or they are just fully inconclusive. You just have a maximum of 25% as well. So I mean, this most likely seems that Alice should choose this basis of what she would get a key, then which are equal to the basis of Bob, perhaps more often, just to get this number. But I mean, for the proof of concept here, I guess that's just fine. So this 7% has to be related to 25%. Okay, so I could show you that this loophole-free Bell test, so even with space-like separated observers, now is really good to make device-independent QKD even between distant users, so that the users are really still this 400-meter away. So, and the question now is, can we go on? And how to go on? And what about quantum networks? Because to me, I mean, the quantum networks are really very nice. I mean, we are working towards this since a long time already, because see, if we have really the option to distribute entanglement between distant users, so like from the top here to the bottom there, then if they have entanglement available, of course, they then will choose some entanglement-based protocol. And compared to the BBM protocol, for example, I mean, this device-independent protocol now just is more inefficient by a factor of 2. So you almost get the same key, but with the option of device-independent. So I would say in a future quantum network, device-independent QPD would become just a standard application. So it's nice. I mean, something where you work, where you put a lot of effort in to make it real, then one day might be just a regular application. But we are not that far yet, okay? So concerning the long distance, we could get a step further on, but the problem here is especially that the light which is emitted from our rubidium atoms is of course not in the telecom window, it's 780 nanometer, which is of course absorbed with very strong probability in glass fibers. Okay, so, and if you do not have special glass fibers, then you of course first have to make this what's called now quantum frequency conversion. So this quantum frequency conversion, what we are using is what's called in nonlinear optics a sum frequency mixing. So we mix the light from the atom, the 780 nanometer, with a very strong bright light at 1600 nanometers in a nonlinear crystal. And then you are generating telecom wavelengths at 1520 nanometers. And these 1520 nanometers, they are just have a very good transmission through glass fibers. And what you have to do is, of course, you have to convert both wavelengths. So in one transmission, only polarization, only one polarization is converted. So you have to operate your converter from both sides in this Sagnac interferometer similar device. And then you really get a very nice and nice polarization maintenance. So the quantum state is really maintained very well. And a similar system was also developed in the Osaka group by Yamamoto and Imoto. And this can be really of high efficiency. So as it works so well, you of course build it also for the second trap. And then you can put effectively any fiber in between, almost any fiber in between, because now you are at the correct wavelength. Okay, so even if our two nodes are still at 400-meter distance, we now guide the light towards the Bell stick measurement via long fiber spools, so really long distances. And then also we wait a while, so that this heralding signal, although it's just a little distance here, still the same distance, but we really wait for the same time what the light would take to get back through some glass fibers. And then if you plot your fidelity over distance, then you see that given the correct waiting times, then you see the decrease in the atom-photon entanglement, and actually the atom-atom entanglement is just then more or less quadratically strong. And yes, of course, I mean, you see immediately that the fidelity here is not high enough anymore for device-independent QPD, at least not in the moment. But because it adds some additional noise simply. But another good feature is that if we just do not send the light through the long fibers, but just wait the same amount of time, then we see that we get the same decrease in the atom-atom entanglement. So in a moment, for these measurements, the fidelity still was limited only by the coherence time of the atom. So, and this actually now already was improved by the Younger team. So they already could implement a different encoding of the atomic state to really extend the decoherence time by a factor of 20 almost. So this is really now more or less new results, which really make hope at least to go over very long distances, like 100 kilometers or something like this, are now possible actually, admittedly with the lower fidelity. So, but the fidelity now is more or less already the decrease of the fidelity with the improved coherence time is now already more due to the noise in the detectors, what we still have. Okay, so in the moment the fidelity would be limited not on any longer by the lifetime of the atom coherence, but rather due to some other noise, which have to be solved. Okay, so device-independent QKD really can be done, but of course, even if over longer distances, we could at least distribute entanglement, but to go to the quantum networks, this is still a long way to go. Even if we now have a longer decoherence time, I mean, if you really would like to have entanglement shared between one node and a distant node, then because of all the protocol, you really need long coherence time. So effectively, one day we really need the quantum memories which even can perform some error correction. I mean, that will be necessary, I bet on it. I guess we never can make a coherence time as long without error correction. And then also these local nodes in between, they have to be able now to connect via also some Bell-state measurements on the atoms or ions or whatsoever to connect the distant nodes. So this is another task. And of course the rates. So the rates, they really have to be boosted either or both by better collection and then most likely also by parallelizing everything. So there is actually a lot of work to be done still, but my people are working hard on it, and perhaps not next QCrypt, but sometime we will report then some better results, some new results. Thank you.
Okay, thanks Harald for the very nice talk. We have time for a few questions. Any questions from the online audience? So if you don't want to speak, you can also write down your questions. Okay, here we got one question online. The question is how much key rate might be obtained by entangled atoms? What is the limit of atom emission frequency? Okay, I mean, you saw that we use this open optics, so just really collect the light via microscope. So this, of course, gives already a strict limit, unfortunately, but I mean, it gives other advantages for the whole experiment. So at the end of the day, I'm afraid we will have to use kind of cavities to get a higher efficiency. I mean, in the group at the Max Planck Institute in Munich from Gerhard Rempe, then there they already demonstrated that they can get the emission up to probability up to more than 10%. And this then gives you, of course, a much, much better rate. But the other limit, what you actually really mentioned correctly, is this emission frequency. So we cannot excite the atom right away. We have to wait for the radio signal from the Bell-state measurement. And of course, I mean, the longer the distance is now in our experiment, the longer we have to wait. And this now actually for our latest experiments on this 100 kilometer to distribute entanglement over 100 kilometers already goes up to a few microseconds. And you have to wait that long. And therefore the rate where you can repeat and repeat goes down. That's why I meant that we will need kind of parallelizing the experiment. So with several atoms at the same time to get much higher emission frequencies. I see. Any other questions?
Yes, we do have a question here on site.
Okay, please.
Hi, I have a quick question here. I'm wondering what is actually limiting the analysis currently to an asymptotic setting? I mean, why is it that finite key analysis is not being done here? Could you elaborate on that?
Yes, I mean, as you saw, we have 3,000 events, roughly. And this now is in 3 days. And I mean, if you think that for the finite key analysis, we need something like 1 million events. Okay, so even Yes, we need 1 million events, and which means that we need 3,000 times 3 days, which is not feasible within PhD, and therefore we stopped the experiment somewhat early. No, but it's again we simply have to get much higher rates. Yes, that's the whole story about.
Thank you. Do I have time for another quick question?
Sure.
So in one of your slides, you actually show 2 p-value bounds for the LHV hypothesis. So I'm wondering, why do you get 2 p-value bounds for a single hypothesis?
Okay, that was for different tests. So one was with the winning game, and then another one was on a different basis on Markovian statistics, etc. So, but
okay,
you can choose the higher one. It's still low enough, at least for me, to say 10 to the minus 9 probability is just very low. That these locally hidden variable theories would be correct.
Okay, thanks very much.
So Harald, I have a quick question. So also in the beginning of the talk, you mentioned people do like Bell tests use trapped ions, also some other groups. So I try to understand from experimental point in terms of quantum network, how you compare the two systems between atom and trapped ions.
Similar, actually. There is a lot of progress in both. The ions, I would say, benefit a lot from the rapid development also for the quantum computer. So I guess there one really perhaps might get such all the operations what you need for these local nodes. So this error correction and then the LSAT measurements for the entanglement purification, etc., earlier. But on the long run, I guess it will be the same. In the moment, I would not bet on either of them. But the disadvantage of the ions, why we never choose them, is the horrible wavelengths that you have to work with. And so the laser technology is much more involved. Of course, there have been tons of improvements over the years. And so I don't know. I wouldn't prefer any of those in the moment.
All right, thank you. I think it's almost the time. Then let's thank Harald again. Then we go to our next speaker, also the last speaker of this session, Professor Nicolas Sangert from CNRS. So yeah, so Nicolas will talk about their experiment on DIQKD. Please.
Do you hear me, Feiyu?
Yes, we can hear you.
All right, you see my slides as well?
Yes, very clear.
So let me thank the organizer first and the program committee for having me here. I'd like to present you a complete demonstration of quantum key distribution of device-independent quantum key distribution. So this is an experiment that has been performed in the group of David Lucas in Oxford. And the theoretical groundwork that was needed to make this experiment possible was obtained in a collaboration involving Pavel Sikatsky from Geneva, the group of Rüdiger Urbanke from Lausanne, the group of Renato Renner in Zurich, and our group in Paris. Let me mention that credits should be mainly given to Jean-Daniel Bancal, Ernest Tan, and Kirill Ivanov for the theory side, and for the experimental side, I can at least tell you that David Natlinger contributed very significantly to this result. So here is the outlook of my talk. So I'll start with some motivation, even though Wenzhao and Harald already talk about that. I'll then show you the protocol and its security proof that we have used in this experimental demonstration, and then I'll conclude with the experimental result at the end of my talk. So here's the a basic slide on the principle of quantum key distribution. We have two parties, Alice on the left and Bob on the right. They are connected by a channel. This channel may be fully controlled by an eavesdropper that we call Eve. And the goal for Alice and Bob is to get the key while making sure that Eve has essentially no information about this key. When the key is obtained, we can use eventually one-time pad to make secure communication, and in this case, the security is provable. We get provable security, and this make QKD kind of unique. So how do we implement quantum key distribution in practice? Well, there are several ways to implement QKD. I'm here showing a way based on entanglement as proposed by Arthur Eckert already in 1991. And it essentially relies on a quantum principle saying that when you perform appropriate measurement on a 2-qubit maximally entangled state, then these yield identical outcomes that are fundamentally unpredictable to any third party. We can thus get a key from the result of this measurement, provided that a number of assumptions are fulfilled. I don't want to comment on all of them. Just mention the last one, which is an assumption on the quantum devices. They need to be trusted and calibrated, and the calibration needs to be maintained perfectly during the whole experiment. So this is a very challenging assumption to fulfill in practice, and deviation from this expected behavior can even be exploited in a number of experiments where the security of QKD systems was compromised. And I'm here giving you a reference to a review paper from our chairman, where a list of proposed and implemented attacks on QKD systems is available. So there are eventually several solutions to get rid of these problems, to get rid of this issue. And the solution that we are focusing on today is called device-independent quantum key distribution. This is here called Bell test-based quantum key distribution. As I'm referring here to Arthur Eckert's paper, where the aim is to derive a security proof without assuming that we know the functioning of the quantum devices that are used in the experiment for getting key distribution. So this is basically now the setting in device-independent quantum key distribution. You still have a source, of course, ideally producing a 2-qubit maximally entangled state, but this is no more an assumption. The Hilbert space dimension is a known, the state structure is a known, so the source is now a kind of black box. And similarly, the measurement are unknown. The POVM describing this measurement are not known, and they are also kind of black boxes. So in our case, we are considering a settings where Alice have the choice between two setting choice that I call XI, and the two choice are called 0 and 1. Bob has 3 setting choice, YI, 0, 1, and 2, and each time a setting is chosen, Alice and Bob receive an outcome corresponding to the measurement result, AI and BI for Alice and Bob respectively, and these outcomes are binary outcomes. So in this case, we want to derive a security proof without relying on the last assumption. And well, the question is, how is it possible? Well, the key ingredient is a non-local game. I'm here focusing on the CHSH game, the one that we use in the experimental demonstration I'm going to show you in a minute. So this is, I'm here writing the winning condition of this game. It's a game having a quantum advantage, but more importantly for us today, when the winning probability of this game reaches a value around 85%, then we know that the measure state is close to the singlet state. This is called the CHSH rigidity, And as I've shown you before, once we know that Alice and Bob are measuring indeed a singlet state with appropriate measurement, then we essentially know that Eve has no information about their outcomes. So this is the basic idea of device-independent quantum key distribution. It has been formalized already in 2009 by Stefano Piranio and co-workers. The main result is a bound on Eve uncertainty about Alice outcomes. This is the graph on the right. As a function of the winning probability of the CHSH game, as you can see, there is essentially no uncertainty for Eve if the winning probability can be obtained by classical means, while Eve has essentially no information about Alice outcomes in case omega reaches the Tyrrell-Sum bound around 85%. So this is, the basic idea associated to device-independent quantum key distribution. Now let me show you the protocol that we have been using. So it's made of essentially two big steps. First, quantum step for raw data generation, and then a few classical post-processing protocols in the second step to be able to extract a key from this raw data that we get in the first step. So let's first focus on the first step, the step where the raw data are generated. They're made of several rounds. Each round is starting with an heralding signal, letting Alice and Bob knows that the system is essentially ready to be measured. Once they got this signal, Alice and Bob, they close their lab to be sure that there's no information leakage to the eavesdropper. And then they choose their settings according to two possible kind of round. First, a test round or a generation round. A test round in which Alice and Bob essentially play the CHSH game by choosing settings 0 and 1. And the CHSH winning probability will then be used for parameter estimation. And the generation round is using the setting 0 and 2 for Alice and Bob respectively, and these settings are such that the outcomes are maximally correlated. So these rounds are repeated a large number of times, and once these n rounds are obtained, then we go to the second classical step, which is essentially made of three big steps. The first step is error correction, which is used to ensure that Alice and Bob outcomes are the same. This is a pass or fail event, and in case it fails, then the devices, they abort. There's then a validation step where we check that the non-local game is one with a probability that is at least larger than what we expect from a previous characterization of the device. This is again a pass or fail event, and in case the winning probability is not high enough, then the system abort. And finally, we use privacy amplification to guarantee that Eve has essentially no information about the outcomes. So let me show you the idea or the way we derive a security proof for this protocol. So I'm mentioning first that we are considering coherent attacks, so the most general attack. And what's nice about quantum key distribution is that the notion of security is extremely well defined. And in particular, it relies on two concepts that are called correctness and secrecy. Let me comment on each of them separately. So correctness ensures that the probability that the system works, that the protocol succeeds, and the key are different is small. And in particular, I'm here introducing epsilon core, which is an upper bound on this joint probability. And the secrecy is defined as the product between the probability that the system succeeds times the trace distance between the actual state shared between Alice and Eve, and a tensor product state in which Alice has essentially a fully mixed state. And these products need to be small, and in particular, I call an upper bound on this product epsilon sec. And and later on, you will see a parameter that I call the sumness parameter, and the sumness parameter is an upper bound on the sum of epsilon core and epsilon sec, which means that once I give you the sumness parameter, this provides an upper bound on each parameter individually. All right, so how do we prove correctness and secrecy in practice? So correctness is validated by means of the error correction protocol, while the secrecy is guaranteed by means of an extractor. And this extractor only works if you provide a lower bound on the smooth mean entropy of the raw data. So let me comment on the error correction first that is used to fulfill the correctness. So the principle is quite simple. You know, at the end of the raw data generation protocol, Alice gets a data, and she computes a syndrome that I call M of these data together with an encoded hash. And she sent this syndrome and the encoded hash to Bob. Bob used the syndrome to try to guess the outcomes of Alice, and then he computes the corresponding hash. They then check that the two hash corresponds, and we use a hash family so that once we know that the hash corresponds, we know that Bob essentially successfully reconstruct the guess of Alice. And therefore, we conclude that the protocol is indeed correct. So let me specify that in our protocol, we use, say, homemade error correction code based on what is called specially coupled low density parity check code. It has the nice property of being universal, and this essentially means that the protocol works for any noise parameters. It requires a minimum syndrome length. Basically, the length of the syndrome that is needed is n times the entropy per round. So this is the Shannon limit, plus a statistical correction of which is given by a prefactor times root n. And interestingly as well, the decoding is easy in the sense that it only increases linearly in time with respect to the length of the syndrome. And for the family of hash function, we use a VH family called VH, which has the property of being epsilon almost universal. Now let me comment on the way we can lower bound the smooth mean entropy that is needed for, making a successful extraction and guarantee that indeed the protocol is secret. So in case you are willing to assume that the rounds are repeated many times independently and identically, a tool has been proposed some time ago, which is called the asymptotic equipartition property, which tells you that the smooth mean entropy is lower bounded essentially by n time the entropy per round plus a correction, a statistical correction of the order of root n. And we know, as I've shown you before, how to bound the van der Waals entropy on a single round from the winning CHSH probability. So this is what we do. We use the data to estimate the winning probability of the CHSH game, and then get a lower bound on the smooth mean entropy through this asymptotic equipartition property. Now, if you want to go beyond this ID assumption to really consider the most general case, as we do in our experiment, then you need to use another tool, which is called the entropy accumulation theorem. It's a tool that essentially allows you to come back to the ID case in the sequential settings that we are interested in here, provided that the number of assumptions are fulfilled. For example, you need to be sure that the setting choice are at a given round are independent of all the rest, in particular independent of the setting choice at previous rounds and side information that is known at previous rounds. And this was fulfilled in the experiment by using a random number generator for producing the outcome. And we also need to be creative in the sense that we need to provide a mean trade-off function, which is nothing else than the worst case von Neumann entropy on a single round, satisfying the winning CHSH probability. So let me specify that in our case, we use a Trevisan extractor. It's a quantum proof and strong extractor, and it has the advantage of the leftover hashing lemma, which is usually used in standard security proof of device independent quantum key distribution, that the seed is exponentially smaller. Now comes the presentation of the experiment. So the experimental setup is here presented on the left of the slide. The principle, has been explained by Harald in his talk a few minutes ago. We're just here dealing with two single trapped ions that are separated by 2 meters. The ions are excited so that they emit single photons, and the polarization degree of freedom of these photons is entangled with the internal degree of freedom of the ion. The photons are then combined at the central station where a Bell state measurement is performed, and a successful Bell state measurement projects the 2 ions ideally in a 2-qubit maximally entangled state. So this is the way we create entanglement. Once this is done, one successful Bell state measurement is heralded, the position of the 2 ions are shifted by a few micrometers to be disconnected from the outside, and then the protocol starts. Okay, so we choose the settings, get the recorded outcome, and so on and so forth. If you want to know the link performance, the performance of this elementary network link, it's represented on the right. So we here see the CHSH core as a function of the number of Bell pairs. So here essentially 2 million Bell pairs have been produced, and the CHSH core is average over 100,000 rounds. You see that it's quite stable and achieve a very high value, higher than 2.6. And the QBER is represented in green. You see that it's also fairly stable, and the QBER is lower than 1.5%. So once this characterization is done, we can basically set the parameters of our protocol so that once implemented, the chance that it succeeds is high. The soundness parameter is chosen to be 10 to the minus 10, and gamma is here the probability to choose a test round with respect to a generation round. The result is the expected result is here represented on this graph. So we see that we need at least 1 million rounds for our protocol to succeed, and in particular, if we take 1.5 million rounds, we do expect to have something like 100,000 bits for the key. So once this analysis was done, the protocol was implemented in practice. 1.5 million rounds were taken, out of this 1.5 million runs, we was able to certify a bit less than 400,000 secret bits. And from these secret bits, we needed to remove essentially 300,000 bits for error correction. So we were left with a bit less than 100,000 bits, which is much more than the number of bits that we use to be able to apply the classical post-processing. And finally, these 100,000 bits were used to encrypt a picture, the picture of John Bell, which is later on sent and decoded by Bob. All right, so here's the conclusion. We made a concrete and practical proposal for a device-independent protocol by designing suitable error correction code, by using extractor and authentication scheme that are very frugal in randomness consumption. In Oxford, an hybrid ion photon entanglement platform has been improved, leading to the distribution of very high quality entangled state between two ions. And as far as I can tell, this represent a record high, what they reported, a record high CHSH value with isolated system with this platform. And these efforts together leads to a first experimental implementation of device-independent quantum key distribution. I emphasize that the security guarantees are valid against the most general attack. Finite size effects have been included. And last but not least, the key that we got at the end of the day was longer than the amount of private and shared randomness that we had at the beginning for making the classical post-processing successful. All right, so with this, I'd like to thank you for your attention.
Okay, thanks, Nicholas, for the nice talk. We have time for a few questions. So Nicholas, maybe I have a question first. So for a theory question, so basically right now we are talking about the assumptions for the quantum device, right? But in DIQKD, we need guarantee the security for the classical device. For example, the classical device have no memories between different ROM, right? So I know there's some work, people think about this. Do you have any ideas to solve this issue, or an idea to further enhance the security for the classical device?
I would say more generally that in my opinion, device-independent quantum key distribution only addresses the assumption that the quantum devices need to be perfectly characterized in standard quantum key distribution. And you're right to say that we are still left with some assumptions. There is the assumption that, for example, the classical post-processing is done in a proper way, in a trusted way first, but there's also the assumption that the systems are perfectly isolated. And these 2 points are not addressed by standard device-independent QKD. And you're right to say that these are also important assumption, and we need to find way to try to get rid of them. But yeah, this is all what I can say. So we're already very happy to be able to generate this key device independently. I think a very important step for us is to try to do the same thing, but with more, say, systems that are maybe closer to commercial system, like photonic system. It would be a very important step. But you're right to say that those questions addressing, the other assumptions are also very important. Yes.
All right, thanks. Any other questions from online audience?
Yeah, we do have a question here on site.
Okay, on site. Very nice.
Nicola. Is that a large fractions of your secret bits have been consumed for error correction, maybe even 75% of that. Is it clear that this can be improved considerably?
Not that much, unfortunately. So, our colleagues from Lausanne already developed a code which has this very nice feature of achieving the Shannon limit in the asymptotic case. And it's even optimal regarding the statistical correction in the sense that it goes as root n. So there's maybe a way to improve that, with the prefactor, but it will, I guess, essentially be marginal. But this also, to some extent, show you how crucial it was in our case to get a very suitable error correction code. Because indeed, when I show you this number, you realize that it's really bit consuming, to correct for error in device independent QKD, and one reason is that all the bits are basically corrected. So error correction is applied not only on the bits that are obtained by the key generation protocol, but also on the test round. Okay, and these test rounds are of course noisy because they are made for violating a Bell inequality, and this is one of the reasons for which a lot of bits are consumed for being able to correct for errors.
Okay, thanks very much.
Okay. Any other questions on site? Online?
We do have another question on site.
Okay, please.
Okay. So here entanglement is established by a shopping experiment on the photon. So why the distance between two atoms is 2 meters? If it is increased, what problem will appear in this setup?
Yes. So you're right to say that in principle, since the entanglement between the two ions is generated by means of detection at the photon level, in principle, you can have longer fibers and increase the distance. That's right, but as you have shown in Harald, and this is one of the steps that Harald succeeded to take, it's not obvious at all because of many effects happening when you increase the distance first. And secondly, when you increase the distance, you essentially have more loss, at least for the wavelength that we are considering here. And more lost means less heralding signal at the end of the day, and less heralding signal means a smaller key, and at some point no key at all. So it's a real effort to be able to extend the distance, and Harald very nicely succeeded along this line. It needs also to be emphasized that the fact that it was essentially not possible to extract a key in this experiment come from the fact that the security proofs that are currently available are not good enough, and they should be improved so that even when you increase the distance and get a low, small data size, we would need to be able to extract a key even in this setting. So there's not only an effort at the experimental level to increase the distance, but there's also a significant effort at the level of the theory to try to improve the currently available security proof.
Okay, I think it's almost time. So let's thank all the speakers again, and I think we will conclude this session. I will see you later in 10 minutes.
All right, thank you again. Thank you, Professor Feihu Xu, for moderating the session. I also like to thank Nicholas, Harold, and Wen Zhao for your presentation. Thank you for joining us. And for now, we will take a short break. Please come back at 4:45 Taipei time. And for the audience on site, we will have some coffee and tea and some dessert outside for you. All right. Thank you. Please come back at 4:45. Thank you.
Bye-bye. Thank you, Hara. Thank you, Nicholas.